once you define the network, another important thing, how to access the parameters. So the GROM block, we have both the network definition and also parameters. So we want to access and modify all the parameters. So here we define a similar MLP as before, 2 dense layers, and initialize it, and given random x, and get the output. Because we have 2 layers, we are using the unsequential, we can indexing each layers by 0 and 1. So for each layer, the dot primes will tell you all the parameters we have. So this is the first dense layer. The parameter is dictionary, which is have a name called dense 0 underscore weight. This is weight, and tell you the shape of the weight. This is the input size is 200. The input size is 20, and the output size is 256. Similarly, we have a bias here. For the second layer, we can access by net 1 dot primes. We still get all this weight and the bias here. Okay. Then, because it's dictionary, we can access the parameters using the string names. Here, I tell you the dense 0 underscore weight. We're gonna get the weight, which is an instance of the parameter. And if you call dot data, actually get the ND arrays of all the elements of the parameter. Okay. So sometimes it's not so convenient to remember all these names. Actually, you can access the bias using the dot bias. So the second layer, the second dense layer dot bias is the parameter, and also the dot data, you're gonna get the ND arrays, all zeros. So in default, we initialize all the bias into 0. Similarly, we can get the weight. This is the first dense layer's weights, and the dot grad will give you the gradients matrix. So this is the gradient matrix with respect to the weight. So it has the same shape as the weight, and in default, all are zeros. So because we didn't do it backward yet. Okay. We can also get all the parameters by connect primes. So this is a network. We connect all the parameters. We have 2 layers. Each layer have a weight and a bias. Now we get a dictionary of 4 items. The dense 0 weight, dense 0 bias, dense 1 weight, dense 1 bias. So because it's dictionary, we can access a particular bias using the name. That's as normal as before. The useful thing here, we can access by patterns, which means all the weights from different layers. So this is dense 0 weight, dense 1 weight, dense 1 weight. The dense 0, this is the first layer, all the parameters you have, the weight bias, so you can get by patterns. Okay. Now about initialization. So at homework, you maybe see that initialization pretty important. If you didn't initialize well, if you run multiple times, you get the random, you get the not so stable results. So we only showed how to using initialize default initializations. Now you can do you can using init to use a different one. Using normal, for example, the normal distribution with the sigma, which is standard deviation, equal to 0.01, and we use force re-init because because net we already have initialized before. If we're gonna call it twice, sometimes usually due to bug, we're gonna generate warning message. So you're gonna tell me that I'm gonna force re-init these parameters. And now we can access the weight, the first layer, the weight and the data, and the first row of the data. You can see that this random variables according to this distribution. Also, we can do constant initialization, which is usually don't happen. You can do that. Okay, I can use a constant equal to 1. Also, you can do for 1. You can just give an ND array. For example, I know I grab this weight from a different network. I'm going to initialize that weight using the other network. You just grab the ND-array here. You can also do the constants as well. The other one that you can specify different initializers for different layers. In default, we're going to use constant. But for the first, in the second layer, we're going to using constant. And in the first layer, for the weight, we're going to using the xvar initializers. That's kind of useful if you have a network have very different parts, and you can initialize one part with maybe with a parameter from another network, and the other ones with random variables. Also, you can do even more fancy things. You can write a customized function to do arbitrary things. For example, I create a class called myInit, which is a subclass of init initializer, and I define the init weight function. So the name, you can ignore the name. This is the layer name, and the data actually the data. What it do is like this function can rewrite the elements on the data. You can do whatever you want. For example, I'm gonna initialize data according to this distribution. So what you can see that I replace data with something here. I cannot dive deep, and then also do fancy things here. So when I initialize it, I can pass an instance of my initializers, and then if I call it, I can show, okay, this is the log message I have. I first initialize dense 0's weight, and then initialize dense 1's weight, and I call this function to pass the data in. Okay, so by this way, you can writing arbitrary. You can use a NumPy. You can modify the weight you want. A more straightforward way that you just you first initialize by random, and then grab the data and modify it by yourself. For example, here I do the dense layer, get the weight, get the data, and all of them plus by 1. And for the first element, I change it to 42, and then I print the first row. You can see that like the first element is 42, and all the others, like at least, is a lot of 1s there. Okay. The last thing here is that we already showed that using unblock, we can share the parameters for different layers. Here we can do that again, but using unsequential. We first create the dense layer. Then, using the unsequential, we first insert another dense layer, the dense layer we created before, and this one, and then pass the primes equals to the shared primes, which means I'm going to create a dense layer with the parameters from the shared parameters, which means these two layers are going to share the same parameters. To compute gradients, we compute the gradient over these two layers and sum them together for the parameter. So that is actually not a copy, just a share. And here's something you can show that if I modify the second dense layer's weight, actually I also modify the third layer's weight as well, because they're shared, just a point. Any questions so far? Okay, so these tricks let you to can do fancy networks and do fancy training ladder, but in most cases you don't need too much.